Extraneous solutions. What are these and how they arise? An extraneous or spurious solution in mathematics is a value that appears to be a solution to an equation when you solve it, but when plugged back into the original equation, it, it does not satisfy the equation. Or essentially, it is a solution that doesn't work in the context of the original problem. How do extraneous solutions arise while solving an equation? In general, extraneous solutions arise when we perform non-invertible or non-reversible operations on both sides of an equation. That is, they sometimes arise but not always. Some inverse operations are squaring and taking square root, multiplication and division by variable expressions, or logarithm and exponential operations. These operations are inverse of each other, but not necessarily invertible or reversible. Non-invertible or non-reversible operations include raising both sides of an equation to an even power. Odd powers are invertible. If we have squared or raised to the power of 2, at some stage we will have to take the square root to get the answer. These two operations are not always reverse of each other. The second example is multiplying both sides of an equation by a variable or variable expression that can take a value of 0. This is done frequently while solving an equation that has variables in the denominator of a fraction. The third type is combining sums or differences of logarithms. All these operations can introduce values outside the original domain of the variables in the given equation. We will now discuss certain illustrative examples. Number 1. Raising both sides of an equation to an even power like squaring. This is a common scenario where extraneous solutions can appear because squaring a negative number results in a positive number, potentially introducing a new positive solution that wasn't present in the original equation. Example A. Solve the equation square root of x plus 4 is equal to x minus 2. To solve this, we have to square both sides. Then we get x plus 4 is equal to x minus 2 whole squared, or x plus 4 is equal to x square minus 4x plus 4. Rearranging terms, we get x square minus 5x is 0, or x multiplied by x minus 5 is equal to 0. This yields two solutions, x is equal to 0 or x is equal to 5. Let us plug each solution back into the original equation. If you put x is equal to 0, we get x plus 4 square root is equal to 0 minus 2. or square root of 4 is equal to minus 2. This is not true because square root of 4 is always taken as plus 4. We always have to take the positive or principal value of the square root while solving a square root. For x is equal to 5, square root of 5 plus 4 is equal to 5 minus 2, or square root of 9 is equal to 3, and this is true. Therefore, the only valid solution to the equation is x minus 5, and x is equal to 0 is an extraneous solution which was introduced by us while you are squaring both sides, and that is a non-reversible process. Example B. The equations x plus 2 is equal to 9 and x is equal to 7 have only one solution, that is x is equal to 7. Square both sides of the solution x is equal to 7 to get the new equation x square is equal to 49. This new equation has two solutions, and those are plus 7 and minus 7. The minus 7 is an extraneous solution introduced by squaring both sides of the equation x is equal to 7. Example C. Similarly, if we square both sides of the equation x plus 2 is equal to 9, we get the new equation x square plus 4x plus 4 is equal to 81, or x square plus 4x minus 77 is equal to 0. If we factorize this term, we get x minus 7 multiplied by x plus 11 is equal to 0, and the solutions are plus 7 and minus 11. Out of these two solutions, only plus 7 satisfies the original equation and minus 11 does not. Thus, minus 11 is an extraneous solution introduced by the non-invertible process of squaring. Before going any further, please like, subscribe, share, and hit the bell so you can be immediately notified for new uploads. It is completely free and only takes a few seconds, and you can always unsubscribe later. Without further ado, let us proceed with the rest of the video. We have already discussed how squaring both sides of an equation or raising both sides of an equation by even powers, we can inadvertently introduce extraneous solutions. Remember that odd powers do not have this problem. Now let us look at another way in which extraneous solutions are introduced into the problem. That is, multiplying both sides of an equation by a variable or a variable expression that can assume the value of 0. This is done frequently while solving an equation that has variables in the denominator of a fraction. One of the basic principles of algebra is that one can multiply both sides of an equation by the same expression without changing the equation's solution. However, strictly speaking, this is not always true, because multiplication by certain expressions may introduce new solutions that were not present before. For example, consider the following equation: x plus 2 is equal to 0. If we multiply both sides by 0, we get 0 is equal to 0. This is true for all values of x. So, the solution set is all real numbers. But clearly, not all real numbers are solutions to the original equation x plus 2 is equal to 0. Only x is equal to minus 2 is the solution. The difficulty arises because multiplication by 0 is not invertible. If we multiply any non-zero value, we can reverse the step by dividing by the same value. But we cannot divide by 0, so multiplication by 0 cannot be reversed. More specifically, suppose we take the same equation and multiply both sides by x to get x multiplied by x plus 2 is equal to x multiplied by 0, or x square plus 2x is equal to 0. This quadratic equation has two solutions: x is equal to minus 2 and x is equal to 0. But if 0 is substituted for x in the original equation x plus 2 is equal to 0, we get the invalid equation 2 is equal to 0. This counterintuitive result occurs because in the case where x is equal to 0, multiplying both sides by x is same as multiplying both sides by 0. And so it necessarily produces a true equation just as in the previous example. In general, whenever we multiply both sides of an equation by an expression involving variables, we introduce extraneous solutions whenever that expression is equal to 0. But it is not always mandatory to exclude these values because they may have been legitimate solutions to the original equation. For example, suppose we multiply both sides of our original equation x plus 2 is equal to 0 by a factor x plus 2, and we get x plus 2 multiplied by x plus 2 is equal to 0 multiplied by x plus 2, or x squared plus 4x plus 4 is equal to 0. This equation has only one solution, that is x is equal to minus 2. We had multiplied both sides by x plus 2, whose value in this case happens to be 0 because x is equal to minus 2. This is an example where we have effectively multiplied by 0, but this is a solution to the original equation and so cannot be excluded. Extraneous solutions can arise naturally in problems involving fractions with variables in the denominator. For example, consider the equation 1 divided by x minus 2 is equal to 3 divided by x plus 2 minus 6x divided by x minus 2 multiplied by x plus 2. To begin solving, we multiply each side of the equation by the least common denominator of all the fractions contained in the equation. In this case, least common denominator is x minus 2 multiplied by x plus 2. After performing these operations, the fractions are eliminated and the equation becomes x plus 2 is equal to 3 multiplied by x minus 2 minus 6x. Or after rearranging terms, we get 4x is equal to minus 8 or x is equal to minus 2. Solving this equation yields a single solution, that is x is equal to minus 2. However, when we plug this back into the original equation, we get 1 by minus 4 is equal to 3 by 0 minus minus 12 by 0. This equation is not valid because we cannot divide by 0. Therefore, the solution x is equal to minus 2 is extraneous and not valid. Since this was the only solution, we conclude that the original equation has no solution. For this specific example, it could be recognized that for the value x is equal to minus 2, the operation of multiplying by x minus 2 multiplied by x plus 2 would be a multiplication by 0. However, it is not always simple to evaluate whether each operation already performed was allowed by the final answer. Because of this, often the only simple effective way to deal with multiplication by expressions involving variables is to substitute each of the solutions obtained into the original equation and confirm that this yields a valid equation. After discarding the solutions that yield an invalid equation, we will have the correct set of solutions. In some cases, as in the above example, all solutions may be discarded, in which case the original equation has no solution. Like multiplying both sides of an equation by a variable or a variable expression can sometimes introduce extraneous solutions. The opposite, that is, dividing both sides by a variable or variable expression, can sometimes cause valid solutions to disappear. This is called missing solutions. We will discuss this in another video. And the last category of operations that introduce extraneous solutions is combining sums and differences of logarithms. Domain issues are the usual culprit in logarithmic equations. Here is an example. Log x plus log x plus 3 is equal to 1. By using the rules of logarithm, we can simplify or combine the left-hand side, and the left-hand side becomes logarithm of x multiplied by x plus 3 is equal to logarithm of x square plus 3x. Therefore, the given equation becomes logarithm of x square plus 3x is equal to 1. Remember, raising something to the power of 10 and taking the log of that are invertible or reversible operations. So if you raise both sides as a power of 10, we get 10 to the power of log x square plus 3x is equal to 10 to the power of 1. Since tan and log are occurring on the left hand side, they will cancel each other and we will get x square plus 3x is equal to 10. If you are not convinced, you can take log of both sides and you will arrive at the same equation, that is log of x square plus 3x is equal to 1. Now x square plus 3x minus 10 is 0. If you factorize the left hand side, we get x minus 2 multiplied by x plus 5 is equal to 0. The solution is x is equal to 2 or x is equal to minus 5. But because the domain of the log operation cannot be negative, the solution x is equal to minus 5 is extraneous or not allowed. Plugging the solutions back into the original equation, that is log x plus log x plus 3 is equal to 1, we notice that log 2 plus log 2 plus 3 is equal to 1 is a valid equation, but log minus 5 plus log minus 5 plus 3 is equal to 1 is not a valid equation. The issue here is that condensing or combining a logarithmic expression or some other types of expression can change the domain. Finally, these are the key points about extraneous solutions. Always check your solutions by plugging them back into the original equation to ensure they are not extraneous. Be especially cautious when dealing with equations involving radicals, fractions, or logarithms, as these are more likely to produce extraneous solutions.